Hey everyone, the goal of this video is to graph rational functions. So by the end of the video you should be able to look at the critical values of the functions to help you form the sketch. So remember, a rational function is a function where you have division of a polynomial. So an example of that is f of x being 2x squared minus 12x plus 10 over x squared minus 8x plus 5. We're going to find some things you already know, and we're going to learn some new things to help us sketch this specific graph. Now, anytime you have a rational function, we always want to look at it in its standard form and its factored form. So the very first step of these problems is going to be to factor the polynomial, or each polynomial. So we're going to start by factoring. I'm going to pause the video and get it factored. You're going to pause your video and do it on your own, and then I'll come back with the answer to check. Good luck. If you successfully factored this polynomial, you should get the following function in its factored form. So 2x minus 2, x minus 5 over x minus 3, x minus 5. And this will be helpful to answering some questions, whereas standard form will be helpful to answering other questions. And we'll go through which is helpful for which. I'm going to quickly power through the stuff we already know so I can spend more time on the stuff we do not know. One thing we should already know is the domain. So for domain, you should think about what our x values cannot be. So our domain is all real numbers except what can I not plug into this function. So one thing I cannot plug into this function is anything that you're dividing by 0. So one thing that would make this 0 is if this were 3, or if I plugged in a 5 here, that would also make the denominator 0. So your domain can be all real numbers, except x cannot equal 3 or positive 5. You can also write that in interval notation, so from negative infinity to 3, union 5 to infinity. Now, the only problem with this is, wait, can't I include like 4? And you can, so this actually needs to be a series of 3 intervals. So I'll edit this to include the interval from 3 to 5 that you can include. So it'd be negative infinity to 3, union, anything from 3 to 5 is okay. That I put parentheses on them means that 3 and 5 are not included. Union 5 to infinity. So the only things that don't work are these boundary points here. That's a very common mistake, so if you do write an interval notation, make sure you write it like that, not this. Okay, coordinates of zeros. A 0 is where your graph crosses the x-axis, which a 0 is where your y-coordinate is 0. So we're trying to figure out what would I have to plug in for this function to get an output of 0. If you think about a fraction, in order to get some fraction equal to 0, the only thing that I really need to consider is what would make the numerator 0. Okay, if the numerator is 0, then no matter what's on the bottom, as long as it works, the whole thing will be 0. So if I had like 0 over 5, that would just be 0. Doesn't matter what's in the denominator, really. So to find the zeros, we're going to focus on the numerator. Now, before we do this, we need to take a look at our factored form and figure out what's going on here. So I factored this, but I really didn't simplify the expression. Anytime you have a common factor in the numerator or denominator, you can cancel that factor. So I can really cancel these x minus 5s, because if you divide x minus 5 by x minus 5, that's just a fancy way of saying 1. So our final factored form is 2x minus 2 over x minus 3. Now, this x minus 5 is important later, but that will be new stuff. So in order to figure out when our output will be 0, I really want to answer the question, when is my numerator going to be 0? So when is 2x minus 2 equal to 0? And the answer to that, add 2 to both sides, divide by 2, you'll get x equals 1. So one of the zeros, or actually in this case the only 0 I will have, is when I plug in 1 to the numerator. So 1 is my x-coordinate, 0 is my y-coordinate. I'm going to write it as a point. Okay, my y-intercept is the reverse. So your y-intercept will cross the y-axis, which would make your x-coordinate equal to 0. So if you plug in 0 for all of the x's, you will find your y-intercept. And I'll do this in standard form just to show we can use both forms here. So if I plug in 0 here, really these are all going to go away, and I'm just going to be left with 10 over 15. So my x-coordinate is 0, my y-coordinate is 10 over 15. Which of course can be simplified, and you always should simplify, to get, let's see, divided by 5, you get 2/3. Okay, that takes care of everything we already know. Let's jump into the fun stuff, which is the new stuff here. So there are some new things we talked about in class, some new things we haven't talked about yet. Let's start with what we've talked about, and those are our asymptotes. Okay, remember, an asymptote is just a line that your graph approaches but will never touch that line. It's like a boundary point that tells you can't go here. So we talked about in class, a vertical asymptote comes from what your, well, let's think about a vertical line first. So if you have a vertical line, your y value is changing everywhere on that vertical line. The one thing that stays the same is the x coordinate. So if this was like x equals 2, x is 2 at all these points, even if your y value changes. So the way we write our vertical asymptote is always an x equals. Now, this is a vertical line. A vertical asymptote, again, is a boundary. So if I were to graph it, it's not really part of the function. It's a boundary line that tells me where my x's cannot go. Now, where can my x's not go in this problem? The answer is my x's cannot be 3, because then my denominator would be 0. So I have a vertical asymptote at x equals 3, because I don't care what the y coordinate is, my x coordinate can never be 3, so it will never be on this line here. And we talked a little bit more about this in class. I'll just quickly recap. If we talked about limits here, so it'll help us define our branches. So one of the branches will shoot off really quickly towards positive infinity. One will shoot off really quickly towards negative infinity. So they'll go in different directions at those asymptotes. I don't know if this is the graph. I'm just making one up. Okay, so to recap, our vertical asymptote is where the denominator equals 0. Next new information is called a hole. A hole is essentially a point that was on the graph, but is no longer filled in because something happens. So a hole is where we have things that were part of the equation but got canceled out. So really, although this x minus 5 isn't in our standard form, it was an important part of that equation. It was a part of our original polynomial. So it's not part of the final answer when you simplify, but it was there to start with and you canceled it. So when you canceled it out, you created a hole. What a hole looks like in terms of a function is it'll be a point that's on that chart or on that branch, but it'll be an open circle. It's literally a hole at where that value would have been, but wasn't because we canceled it. So it looks something like that. So our hole is a point, not a line. And the x-coordinate of our hole is whatever the x-coordinate of that factor you canceled out is. So if x minus 5 equals 0, the x-coordinate is 5. In order to find our y-coordinate then, what can we do? Anytime you want to find a y-coordinate, you have an equation here that solves for y, so you can just plug it in and figure out what that's going to be. If you think about it though, if I plug in the 5 to my original problem, remember this was my original problem in standard form, or in factored form, we would get a 0 in the denominator. So in order to find the y-coordinate, we need to plug it into our final simplified form, which is actually a lot easier for us anyways, right? So I'll plug in 5 to this equation and see what my y-coordinate is, and it'll give me the y-coordinate of my hole. So I'm going to pause the video and do that computation. You do the computation on your own, and I'll come back with the answer. Okay, so to find the y-coordinate, I got 8/2, which is just 4 when you plug it in here. Now note that I'm not writing down what the vertical asymptote or the hole is. I'm not writing down how to find it. I'm just writing down this example. I expect that whatever I'm saying, you're taking the notes you need to take to be successful on future problems. So if I'm saying something, write it down. And if you're thinking, oh shoot, I didn't write down what she said, rewind the video and go do it. Okay, last piece of information is other asymptotes. So in class we talked about 2 different kinds of asymptotes. There's a vertical asymptote, and then we could also have a horizontal asymptote. So that would look something like, I have a horizontal line, I have a vertical asymptote as well. It'll give you the boundary for where those branches should be located. Now, it's not always going to be horizontal. You actually have 2 options for this other asymptote. You can also have what's called a slant asymptote, which is exactly what it sounds like. Instead of having a horizontal asymptote, you might have one that looks slanted, or just like a line. It would look something like this. So there's 2 different options, and the way you figure that out is by looking at the equation. So let's look at standard form and figure out what this means. I actually want to go back to the picture to make sense of this idea. This one's a little bit trickier than just the vertical asymptote. A horizontal asymptote, if that's what we have, is going to be a y equals something. Okay, so we're looking for a line where our y-coordinate stays the same as our x-coordinates are changing. Now, if you think about it, our graph is going to hug that line in some way that looks like this, and I'm just making up an example so we can talk about it. So what we're really looking for is as our x's get either increasingly really, really big or really, really small. So as our x's are approaching infinity on either direction, so approaching infinity this way or approaching infinity this way, what value are they going to, I like to say, hug? So what value are they going to get really, really close to but never touch? So our x's are going to increase forever and ever, but they're never going to touch whatever this horizontal asymptote is. Now, if you think about the equation, if I plugged in increasingly big numbers for x, we can figure out what's going to happen. So if I plug in really, really, really big numbers, it's not really going to matter what's going on here because it's just going to be really big. So really what you're going to have is like 2 times, if you square a really big number and multiply stuff by a really big number, it's just going to be 2 times a really big number over, and it doesn't really matter what happens here, this is a 1, so this is all going to be a really big number, and you're going to be multiplying that by 1 times a really big number. So you're going to have like, and this is hard to think about because infinity is not a tangible number, but this is the best way I can think to explain it. You're going to have 2 times a really, really, really big number and 1 times a really, really, really big number. Maybe it's not infinity. Maybe that really, really big number is like a trillion. You have 2 times a trillion over 1 times a trillion. So the horizontal asymptote can be found by the ratio of the coefficients if the degrees of the numerator and the denominator are the same. So since these are both a degree of 2, they'll kind of get increasingly big at the same rate, and we can just look at the ratios. So our horizontal asymptote in this case will be at y equals the ratio of the lead coefficients, which is 2 over 1. Or you can just say y equals 2. Another way I like to think about these is you can actually figure this out by doing polynomial long division. But I can even be a little bit more specific and just say if I divide things in, eventually I'm really just going to get to the point where I'm dividing 2x squared over x squared. If I simplify that out, the x squareds are going to cancel and you're just going to be left with 2. Now the reason I'm talking about it this way is it's going to help you with the back page when you are figuring out the other 2 cases. So the case we are right now is where the degree of the numerator is the same as the degree of the denominator. That's case 2. Then you'll have a horizontal asymptote at the line y equals a over b, where a and b are the lead coefficients. There are 2 other cases. One is if the degree of the numerator is larger, which is case 3, n is greater than m. And the third case is when the degree of the denominator is larger, which is case 1. And here are notes for what's going to happen then, which I'm going to have you kind of think about as you do these problems on your own. So we'll come back to those a little bit more in class. This is kind of confusing, so we will talk about this more, I promise. Try to construct your own understanding of that for now, and for the sake of time. The last step would be to use all this information to sketch a graph. So I have a vertical asymptote and a horizontal asymptote. Those are helpful to setting up boundaries, so I'm going to start with those. My horizontal asymptote is at y equals 2, so I'm going to go ahead and draw that line. My horizontal asymptote is at x equals 3, so 1, 2, 3. I'm going to draw that line. Here are my boundaries. It's going to tell us where our branches are. Can also plot my hole is at 5, 4. So here's 5, here's 4. There's going to be an open circle there for a value that was canceled out. My y-intercept is at 0, 2/3, which will be about right here. And my x-intercept is at 1, 0. So let's see, here's 1, 0. And from this you can sketch a graph. It's a pretty generic graph, and I don't really know enough information to know the shape. But any rational function has multiple branches looking something like this. It can have 2 branches or 3. It depends on how many asymptotes you have. In order to get a more specific graph, you would need to make a table of values for each branch, which the video time is almost running out, so I'm not going to do that. I suggest you do that on your own paper and get a better sketch than what I have. But you know it's got to be up here because the hole's up here, and you know there has to be another branch down here because of the x and y intercepts. So that tells you, what quadrants or what sections of the graph that will be in. Again, I know the asymptote thing is kind of confusing, so try these problems on your own and construct your own understanding of cases 1 and 3, and we will talk about it more in class. Have a good night.